Well, greetings and salutations, everybody. This is Silent Movie 7. Feel free to read this. This is all the data that I'm going to be using in the modeling that I'm doing today. I am measuring out uh, the observation to 5 different points. I'm going to add a building. There's that tower in LA to that one. You'll see that in there. The points that I'm going to be measuring out are from the observation point uh, to these 4 locations. Now, I called this one Sly's Peak. It's the little peak that you'll see here in a second. Only because of the fact that I couldn't find a label for the name of the mountain, so I'm claiming it. Haha, it's mine. Anyway, but I'm sure it has a name, and no, no offense meant. Um, Also, what I'm going to be doing, which is going to make this take a little bit longer than usual, is I'm going to be putting the terrain in, just basically some average heights, uh, as seen in these images here. I'm going to be adding these images to the background, stretching them out to the distances that are stated. And what you can see here is these are the elevation profiles. I don't know why this one did this for LA. I really don't. That's actually the ocean floor for some reason. It's really kind of weird, but well, or at least it's just a lot higher than it's really exaggerated. So and but this here is what do you call it? This here is 0 meter right here. And I did that. The arrows indicate where the shore starts, so I know where to cut off the terrain. These are the ones for more locations. And yes, depending on which direction you start the line from, it makes it go one way or the other. So my bad on that. I have to compensate for that later. And then, of course, the last one to what I'm calling Sly's Peak. Um, there's been a lot of discussion over the past day over, terrain in the middle is supposed to be covering everything up, even though Jaron said that it wouldn't be seen at all. Um, Obviously, we're going to examine that. And quite simply put, I'm going to compare it to this image. Okay, this is Anderson Peak. This is, St. George. And then, of course, on this one, this is St. Jack. And this little sucker right here, I'm calling that Sly's Peak. Cool? And like I said, these are the images. I've isolated them from the footage. And I'm going to be comparing them at the end of the video. So if you are watching this in the recorded sense, um, and you are not really interested in how much work this is to do this, you can skip through probably to about the last 10, maybe 15 minutes when I'm actually comparing all the images that I make, the renders that I make in 3ds Max. Something else I should point out once again, uh, the program called Gmax, that's spelled GMAX, is available on TurboSquid. All you have to do, and it's available for free. You can do exactly what I'm about to do, with the exception of it won't do an end render, but you can still get the data by looking through a camera and then making a capture of the viewport that you're working in. You can do that 100% for free. Use the exact same method I did and check all my work. Okay, so with that, I'm going to be going silent and getting starting to work on this, and that's going to be the rest of the silent movie. So see you at the end. Okay. Oops. Let's go a little bit louder here. There we go. Okay, so for those who weren't trying to engage with Pete in the chat, the I just modeled out in 3ds Max what it would look like. This is the flat camera. This is the curved camera. Okay, what those you saw me do a little bit of adjusting on the zoom level because I had the zoom messed up, and I also mislabeled cameras at first. So anyway, these were the mountains, and this is the what's it called, Wilshire Grand, something like that, tower in LA. Model them out. This is what it looks like basically. And then we have, like I said, the flat camera. Okay, one across a plane, one across the measured and predictable curvature. And then what I did was I took those renders, I put them in here. I compared them to pictures that were in the footage produced by Jay, whatever his name is, and Jeranism, and or mirrored by Jeranism. And then what I did was I used as a measuring point to get the scale of the picture. As a measuring point, I used that Wilshire Grand Tower here. Move to the side here. That is this spire right here. There is a, if you see on the left side of my cursor, actually I'll zoom in a little bit further. Okay, this dark colored building with this spire on the top, that is that tower. So I used this red area is the height of it. So I used that. The image was about 1 degree off, so I had to compensate for that. Y'all saw me do that. And then all I had to do after once I had something that I could measure against, then I knew the scale of the picture. And the Anderson and George peaks, which are the green ones, and the green one and the blue one, they matched up just fine. Off by a little bit, but I'm not counting refraction, so it's just a little bit of stuff going on there. But basically, they are both of equal height, or just about equal height, as it is in the render. I'll show you that here. Oops, nope, not there. This is on the flat cam. This is on the curve cam. Okay, they're both damn near equal height, even though they're different distances and different heights. Okay. And then, drop that. And then without changing the size of this, because now I have a scale, without changing the size of the picture, I put this here, and I got Mount Jack and what I dubbed as Sly's Peak. They matched up also just fine. Pretty simple. And as you can see, there's a lot of discussion of how much land is supposed to be in the way and all this from all the bits of terrain in the beginning. I think we can all agree just by noticing how little of that there is going on here. It's not even a factor. I could go in, and I was actually prepared to go in and put in the land features there, but none of the land features are high enough to block it out of the way. None of them are. I mean, literally, none of them are. If you look at this, for example, here, there's like nothing in the way. There's this little clump right here, but that's not even high enough to get in the way on flat or globe Earth. Okay, and that's basically the same clump. This is that little clump there. Well, it's actually a part of the extended part of it, a little bit further east. This is a smaller part of it. It's not even significant. It's really not. So, and then matching it to the flat camera. Now, if you look, I got both of these at the same scale, matched up against the building. Same scale, matched up against the building. The brown spot here is the land above sea level. I think it was like 86 meters, 82 meters, whatever I did. 86 meters. And match that up, and look what happens to the peaks. The peaks don't match. Period. The peaks don't match. Not even close. Not even partially close. And I did I did rotate the camera the image just as I did with the flat one or with the curved one. So didn't match. And then using that exact same scale, doesn't matter where I put. And what's funny is the horizon actually goes up even higher. If I put the brown of the land below Los Angeles somewhere, anywhere here in this land, okay, the 86 meters, anywhere here in this land that you can see the land, it doesn't even come close to matching up to the two peaks. Doesn't even come close. So ultimately, once again, somebody has provided some absolutely awesome footage that if you go out and actually check it and do the work to model it out. And like I said, I didn't build the model to the picture. Okay. I built the model and compared it to the picture. So, and y'all saw me do that. I'll show here to the front. Okay, these are the two models. This is the curved model. This is the flat model. And let's you know what? Which one's got the highest one? Hold on. Which one's got the highest obstruction from that mountain set in the beginning? That's going to be this guy out to St. Jack. All right. So hold on a second. I'm going to find out how high that is and how far away it is. And I'm just going to show you because that's the highest point in the middle. That's the only thing that would have any kind of contesting to the observation. So we'll do the elevation profile. Okay, and it needs to be right there. So where is that? That's right here. How high is that? Highest point there, that says about 491. Oh, 504. On this hill right here. Well, that seems to be the peak of it, but it's not the line. Well, we'll just go by the peak of it. Screw it. 541. See that? 541. This is San Juan Hill. Okay, so 541. And what's the distance out to it? I'll just show you. Okay, oops. Meters from the observation point. And then in a second here, I'm also going to lower the camera because there's discussion of where he was standing. And it seems to be that he was standing right here, which is really not making a whole heck of a lot of difference. Or it might be down here, but, you know, we'll check that in a second here. So let's get this out. The distance, San Juan Hill. The distance to San Juan Hill. I'm trying to keep it parallel to the peak there. Okay, 99.251. 99.251 at 541. Okay, so what I'll do here, I'm going to put a tape in. Move this all the way over. Okay, so it doesn't matter where this is. This is just going to get the distance. 99.251. And how high was that again? 541? And we'll go for the peak of it. Yeah, right around 541. Seems to be it. We'll put it in a little box. Oops. Let's see. So, yeah, that'll be 0.541. We'll do a width of 2 kilometers. Oops. Wow. Didn't mean to do that. 2 kilometers. All right. And then we'll measure it right down here. And we'll make that white. And that, and one. All right. We'll do that, and then I'll also put it up on the curved one. Okay. So, let's see. Cameras, flat cam. That's how much of it's going to cover it on the flat cam. Still got the problem with Los Angeles being lower than it. And pretty much that would basically mean that you would have to see land here about as high, almost as high as the towers. Okay, from this viewing point. And then go over to the curve cam. Look, it is not obstructing the view of any of the mountains at all. So, and that's the highest point between them. That is the highest point between these guys. So, not really much else to say there. So, ladies and gents, I was peppered a couple of times today to model this out, or somebody, well, a couple of people kept on coming at me with bad math, and it doesn't match. It doesn't match anything flat Earth. It doesn't match at all. Okay, no match on the Anderson and yeah, George, and it doesn't match on Jack and Sly at all. But does match on yeah, it does match on the curve for Jack and Sly, and it does match for Anderson and George. So thanks a lot again to the guy J Tone or whatever his name was, and thanks a lot to Jaronism for actually making it so I could see this video, because I didn't see it any other way. And yeah, Fino, ha 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 ha. But you know what, Fino? Hold on a second here. There you go, Fino. Have fun, Fino. I got you got some power now. But that's all I really had, and I was just going to model it out. And how far should the mountain fall behind the curve? You want to see, Pete? I'll show you. Oops. Wow. Yeah, if I pull up the right program. This much. All the mountains here should fall behind the peak, or the each mountain should fall behind the curvature their respective amount this much. You see, are you watching, Pete? You know, because I'm not going to put a picture of the entire night sky on one of these side of these mountains and think it means something. At 123 miles, what are the curve calcs? Here's the thing, man. No, I did the curve calcs, but nobody was satisfied with that, so I modeled it out. The curve calcs you'll find in the previous video to this, Pete, if you'd like to go over there and watch it. But nobody was satisfied with that. They were like, "Oh, but there's stuff in the way and all this other stuff." And guess what? There isn't. And guess what else? All of the peaks match the curve. None of the peaks match the flat Earth. Just give the figure here and which one? Which mountain? Which mountain you want, man? That's right, Tommy. My fellow 3D'er, you're a tool. There's also one other tool I'm giving out right now. Been around me for a while. I don't know why I didn't do that before. The 123 G, Pete. Which one is the 123-mile mountain? Nobody tell him. Which one is the 123-mile mountain? Or are you just echoing somebody else's words because you heard 123-mile mountain? Petey, come on, answer the question, bro. I just wanted to do something else here while I'm waiting for Pete to not answer. Cameras, flat cam. By the way, this is, let's see, the curve cam. Watch what happens when I move this down. This is all the way down at the water line. Okay, the only one that I would lose at the water line is Sly's Peak. This is about 100 meters. And this is, oh wait, no, shit. That's even less than that. Did Pete answer yet? No, he didn't. Let's, here's something you need to see. The green line stops up here. That's 200 meters. This is sea level. Now, I'm moving the curve camera right now. I can still see Sly's Peak, okay, my peak, with the obstruction in the way of the highest point of San Juan Hill, which goes behind the curvature before the mountain does. Before the mountain does. I don't even pay much attention to this stuff. Then what are you doing here, Pete? Okay, so let's find out what this distance is, huh? So I had it at 200 meters. Is this let's put that at about 10 meters. Nope, guess not. Maybe 20? Or no, excuse me. That's I'm sorry. 2 meters. No, that's 20. I got the decimal in the I'm sorry guys, I'm tired. That is 2 meters. Yeah, that's 20 meters above the water right there. 20 meters. Okay. 20 meters. I think I had 200 on there because of I was thinking about something else. But as you can see, you can still see it. And obviously you would still see it all the way down to the water on flat Earth. But now let's do something here. Smooth highlights. I got that smooth highlights wireframe. I wonder how far I would have to be down to get Anderson and George to be even, as we see in the picture. y'all, y'all seeing the problem yet? Oh, that's a good little bit. How far is that? Tape. Don't specify length. Gotta be, just to get those two peaks to be the same height, I gotta be 2.5 kilometers below the water. Sorry, Pete. No. And the reason why I'm not bringing up the Earth curve calculator, because I did it yesterday, or was that yesterday? Day before, whatever. I already did it, and B, I modeled this out without an Earth curve calculator, just using the tested and known radius of the Earth, which I am testing here, by the way, when I model it out. So, it's pretty simple. You know, I don't need the Earth curve calculator when I can model it out, and you can too. Make sure you go out and get the program called Gmax. Just give the drop. Why? What's the point? Or do you want to see if my model is actually matching what it says on the Earth curve calculator? You see, I don't need it. I really don't. Petey, I'm talking to you, bud. You cannot, because you know that none of it should be seen. I just showed you that it's being seen just fine. Okay. You need to also understand that drop is not hidden. Drop is drop. That's where you get it from the Pythagoras theorem. But drop is not hidden, moron. Just like putting a picture of the entire night sky on the moon doesn't mean that the craters match up and are somehow related to the moon. Yes, he tried that, by the way, guys. That was hysterical. Well, I guess Petey's not going to answer anymore. Or at least he won't answer me anymore. Oh, there it comes. The Milky Way on the moon is one of the greatest in history, and you know it. Yeah, it was hysterical. It was one of the funniest claims I've ever seen in flat Earth. I'm sure you have moved on since then. Stone Monkey. Right now, I was dropping the camera around to get different heights, just to show that it was how low I could go and still see everything. And I think I have it right now at 20 meters. Well, on the curve calc or on the curve cam, on the flat cam, to get these two mountains even as it's seen in the picture, I had to go over 2 kilometers under the ground. Yeah, okay. So Pete, you're not going to answer me, are you? That's fine. You don't even know what you're asking for, but yet you want to ask for it. Oh, for the on the photo, you mean? The photo, I have it at what, 62 meters, but they said it was a little bit lower than that. That's fine. I showed that you can go all the way down to 10 meters and still see everything just fine. But you know what? You know what I'm gonna do? Watch this. Just because I'm an ass. Let's see. Distance in miles, 1, 2, 3. Okay, so anything at a distance, let's see. Okay, so just because I feel like having fun. Here's the drop. I'm going to change this over to meters. Here's the drop from that distance. It doesn't matter what height you are to get drop, because that's not how drop is measured. Drop is measured as a tangent from the surface. So I could put in 500 miles or 500 meters in the air and the drop does not change. Okay. Now, now already 3075 is only higher. The only thing that's higher than, these are the heights of the targets. The only thing that's higher than is Sly's Peak and the Wilshire Grand Tower. Okay. So, number one, three of them already beat it. But just to show you that my model represents that, all I have to do is take this, go to front, and then I'm going to make sure I have a horizontal line. And now I need to go to the middle of this so I can move it around. Then I need to go to this to make sure that I'm hitting it right. Okay, I guess I gotta zoom out a little bit further than that. Oh, that went fast. Okay, this is on the curve one. Now I just matched this line, this orange looking line, up to it. And look, the only one it beats is Sly's Peak. Okay? The only one it beats is Sly's Peak, as stated. Oh, and it beats, hold on. Well, it doesn't beat the tower because of the fact that uh because of the curvature of the earth, but it would be if that distance was the same. So even if you were at the water line, okay, at the water line. Now, you probably want me to measure the drop. Oh, tape. What was that drop level again? 3075, huh? Well, let's see. Now at 123 miles, that's this guy right here. You know, the mountain you don't know the name of, but want to just sit here and quote him. Okay, so what I need to do is, I'm just going to bring it all the way up to the peak here. I'm going to have a little offset. Now it was 3075. Oops. Go back down to the bottom of it. Okay. Now I have this at 3.075. Now this is going to be off by a couple of meters because of the length and how this is all measured out. Oh wait, no, that's got to be that's actually got to be vertical, but you know, whatever. Yeah, I'm off by about maybe 2 meters. 2 meters. Hey, Petey, look on the screen, man. Off by maybe about 2 meters. And up, you know what would be actually kind of interesting to know? No, I'm dead on it. I'm dead on it here. So, Petey, even the thing that you were asking for, I just showed you. So, anyway, guys, all the measurements work out, and thanks to Pete, it also I checked it out on Metabunk on this one as well. So it works just fine. Even from if you had your eye at the water line, you would still see. You would see over San Juan Hill, because that's what this orange line is now. It's a tangent from the water level at the observer's point. You would still see Anderson Peak, George, and Mount Jack. You would still see it. The only one you wouldn't see in the stuff that I modeled out was Sly's Peak. Cool. So that's all I got, ladies and gents. I hadn't even planned on making it this long, and the reason for it being silent is just so I could work and not have to try and talk my way through things and all this, because everybody hates to hear my voice anyway. All right, so all good. All right, so ladies and gents, thanks for stopping by. Eye at the waterline. You see many tens of miles nonsense. Whatever, Pete. You don't even. I just modeled out. I just did your line for you, and you didn't even pay attention. So, you guys have yourselves a great evening.